It's my great pleasure to introducing our own Caltech advisor, Adam Wierman. So for those who started our work at Caltech after 2007, I think almost every one of us has been mentored by Adam in different format. Like Adam joined Caltech in 2007, and since then, Adam, Steven, John have been co-advised many of us, like in many different topics, either energy system, data centers. You're not advising? Okay.
I do the recruiting.
Adam, yeah, John have more stories to share, but let me continue. It's actually always been like a great opportunity for us to having three, actually also Richard also helping a lot, having so many advisors looking after us. So they've been working on many different topics, data center and online operation, online control, and I think you can see from today's talk, we have been working on so many different topics. And even if we are not advised or co-advised by Adam, Adam is always willing to help. So he always inviting us to go to present his group. He will teach us how to write paper, even he's not co-author of the paper. He will teach us how to do the talks. And no matter how bad our first version is, he has magical advice to making our talks and the papers become great ones. Thank you so much, Adam. And Adam's mentorship did not stop at Caltech. So I joined Caltech 2007. I was lucky to study at the same year when Adam started his career at Caltech. So I got opportunity to observe how Adam really started his group, expand his impact, and smoothly got becoming a tenured full professor within 5 years, 1 year earlier than I graduated, got my PhD. So that means that although he has been a great role model for many of us, when I started my job at Harvard, many times I was kind of, what should I do? I was kind of thinking what Adam will do if Adam in this situation. But as you can imagine, I was not able to figure out what Adam would do using my own mind. So rather I would just call Adam, asking Adam, what should I do? As always, Adam will just patiently listen and then share his wisdom with me. So without advice, I think my life at Harvard would be much harder. So thank you again, Adam. Without further ado, let's welcome. Looking forward to the talk.
Okay, I really wasn't expecting that. Thank you. Yeah, it's a great pleasure to be here and to get a chance to talk. I was thinking of how to start, and I must say I consider myself one of Steven's students too. So, I started at the same time as Lena, and maybe she was learning from, but I was learning from Steven and Manny that whole time. And Steven in particular, I think we've heard about his transition, and I mean this is something that's really amazing. He had a career in networking and distributed systems and just decided to, one day, to wildly switch fields to something that he hadn't studied before, and then became just as much of a leader in that field, as he was in the original. I mean, that's phenomenal, and I think as a junior faculty member starting here, to see someone make such a fearless transition really opens your eyes to what you can do in your career and broadens the idea of impact and the idea of choosing directions and opens the door on a lot. And then the model for all of us that Steven has really demonstrated throughout his career is theorem, prototype, startup, and amazingly repeat, repeat, right? I mean, doing this once in a career is amazing, but doing it time and time is really incredible. And so I think these two things really shaped who I am as a faculty. So thank you, Steven. And so today, this is kind of one example of that, and I feel like as of this spring, I finally graduated from Steven's tutelage because I finished that loop once, and so this is kind of a story of that process, which is fun for me, and hopefully you enjoy. There's a lot of looking back. There's a lot of slides that Nianzheng and Zhenhua and Minghong made during their points in the career with me that I went back and culled and are in this presentation today. Okay, but starting with today, if you pay any attention to the news, you see articles like this basically every day about how much energy, how much water, how much noise, all of these things that are associated with this AI boom that we've been hearing about so far. And I always like these little tidbits, factoids to help put it in scale. So at this point, within the last 12 months, data centers have used 50% more energy than the whole of the United Kingdom. So that's an amazing number, and it's passing more and more countries. I think Argentina it passed as well now, so it's getting bigger and bigger countries that data centers are equivalent to in terms of their electricity usage. And we used to talk about small percentage. You don't think of these things as a big deal within a national economy. In Ireland right now, it's 20% of the electricity usage of the country is devoted to data centers. In the US, Virginia is at about 25%. The Bay Area is at around 40%, I believe, by some estimates. Right? These are massive percentages of our energy ecosystem in different locales devoted to compute. An interesting question for later on. If you think to yourself, what is the right percentage of energy generation that should go to data centers, AI, training? Like, what is that number? I've asked that to people. There's wildly varying answers that people will give in terms of what you think of the societal benefit and the payback you get from these things. But at this point, it's not a rounding error, right? It's a major component. And this is a slide that came from David Brooks and Ben Lee that emphasizes it's not just the operational costs as well, right? So the fabs, the data centers, just the companies listed here are each about 2x of New York City's emissions, carbon, and electricity usage, whatever measure you prefer to use on the right there, which is incredible. And then I think Zhenhua mentioned one of these numbers already, but you can compare it to a Google search query. If you're a low-end bar, this is a safe estimate. It's like 1.5x per inference, even with an old model at this point. The new models are much higher. And if you take the upper-end bar, you're talking 30x in terms of the energy cost comparative to these things. And now we're doing these constantly. Like each keystroke that we type into Google is doing one, right? If you compare where we are today compared to 3 years ago in terms of the energy cost of doing what we do with AI and machine learning, just the fact that we're using LLMs now, 30x more energy demands to use that type of ML tool as compared to more traditional approaches. And the numbers are growing dramatically. Those are 3.5x numbers. When you go to 4x, you're talking 100x scale in terms of the energy demands of this. So multiply across the board by a very big number, and you see where we are today, and it's going to just keep growing from here. So this is a big deal, and the numbers are absurd. I remember when we started working in this space, we were talking about 20 megawatt data centers as big. Now you see news articles talking about 5 gigawatt data centers. Yeah, go for it. You're going to pick on the numbers, right?
Yeah. Is it inference costs or?
So this is inference, this is training.
And the training should be amortized across.
Yeah, and so this is just inference. So this is not combining the two. Yeah, so it could be worse. I'm trying to be low end on these comparisons. And there's some nice, if you want to look at the details, there's some nice citations of how people have gathered these. Okay, so it's big. That's what the news shows. What you might not be aware is how much backlash is starting to come to this, especially in local communities where the data centers tend to be sited most often. And so, Phoenix, Portland, Northern Virginia, there's, every time a new data center goes up, there are protests that are starting to happen around this. Part of this is the noise coming from the data center, which you may not even realize is a problem, but these are loud. And so the local communities have to deal with noise pollution. But another one is the energy costs. Utilities are not very good at understanding how this is going to impact local consumers in terms of their prices. And depending on the market impact, depending on the energy generation, depending on how the profiles of energy uses impact prices locally, you see significant increases in prices for the communities where these are placed. And these don't even mention water, but there were massive protests around water usage when you build a data center in Phoenix, for example. And so there's enormous backlash happening. And utilities at this point are just giving up in many places. So I have Amsterdam for 2 years. I think this has been lifted now, but for 2 years they had a moratorium, just no building of data centers. Ireland just recently, this was a slightly old one, but just last week completely pulled the plug on new data center construction in the whole country. EU is looking at major relegations where you put data centers into categories based on what they're used for, and the low-end useful to society data centers just won't be allowed to be built, and the other ones will have different queues for timing for construction based on their proposed usefulness to society. Singapore is frozen. Northern Virginia, where most data centers in the U.S. Is getting to the point where 5-year, 6-year interconnect queues if you want to build a data center in these regions because they just can't handle the new load that's associated with them. And so it's becoming even hard to build in terms of getting the energy. And this is the beginning, right? The next decade is going to be much, much more energy usage. So this is a forecast. So this is growth in data center over some window, what the projections look like. They're relatively steady until boom, last year, and you've got a massive, massive growth in what's coming down the pipeline. And this is my favorite one. This is some work that I did when I was consulting with SIP, and this is what the forecast looked like in 2001. So you see like about 1% of annual electricity consumption in the US, and it's staying reasonably steady, growing a little bit, but this is 2030 at the end, so this is a pretty long horizon. This is now. So notice the change in scale from 1 to 2 to 3 to 4, 5%. Now we're talking 5, 10, 15% global on that same horizon. And so the plot from before was this band. This is the new projections for growth and installations based on actual proposed data centers that are live in interconnect news now. So yeah.
What happened to the end of CMOS?
You mean where are these going to actually come? There should be a big. That was not modeled in this. From my perspective, when you see these numbers, this feels very familiar to when Stephen and I were thinking about energy and data centers when I first arrived at Caltech. So this was the plot that was in every talk at that point. You probably had this in some of your talks, right? So this is a plot from 2000. I think 7 or 6, I guess the numbers were 6, so it was electricity usage from data centers in the US, and there was a big study trying to make forecasts for how they will change and what could happen if we did, different integrations and focused on energy, and people were worried about it, growing up like that, but the argument was that if we push the research, we can actually drop it, and there was a big research push across academia and industry to try to get to that point. And this was really a big push. I like this quote because I used this in my talks back in the day, like in the early teens, and now it became true, right? He had a lot of foresight at Microsoft, right? Despite our best effort, despite all the research that we did, it is among the largest users of the planet. And even at that point, there were more emissions from data centers than the airline industry. And look at what's happened since then in terms of the compute. So this was, I was looking back at all my slides, the last few days, and this was my intro slide from 15 years ago at this point, arguing how bad data centers were and how they were in terms of, this was a very short flight, like a 45-minute flight. And now we're talking 3x, 10x more for each of these because we're using LLMs, right? And these other industries have gotten more efficient while this is getting less, right? So we're talking a massive change. And at the time, there were the same sort of news articles. I remember being interviewed by New York Times where they were like big thing on how internet and data was leading to all these power. And so the same sort of story as we have now was happening then, but we were at a much easier stage, right? The buildings at that point ignored power entirely. So the measure that was used, that was invented around that point, was power usage effectiveness, PUE, which was the power coming into the building over the power that went to the computing. And at the start of this phase of research, it was like 4. You wasted 4 times the amount of energy, or 3 times the amount of energy that you actually used in the data center. And by the end of that kind of wave of just optimizing the building, optimizing the power conversion, optimizing the AC, optimizing all those things, it got down to 1.1, which is still about industry standard today for most companies, depending on the region. But we were making the argument already back then that this is a slide from back then, that PUE was not the right measure. How do you make PUE better? You just waste more power, and then it gets lower. Make your computing less efficient, and your PUE drops, and also has nothing to do with carbon, nothing to do with environmental impact. And there's Jevons paradox, one of my favorite paradoxes to sort of highlight the dangers of just focusing on energy efficiency, which is, it's wholly a confusion of ideas to suppose that economical use of fuel is equivalent to diminished consumption. But a picture says it better than the quote. If you take your typical demand curve, cost usage, if you drop the cost, what happens to the demand? The demand goes up, right? You can't avoid basic laws of economies like this. And so, that's kind of exactly what has happened. We've made things much more efficient. That doesn't mean we've made them more sustainable. So, in our work, and this was the focus for a long time, a big focus in the group was, can you achieve renewable data center running on renewable sources? It certainly seems impossible. And now these are Zhenhua's slides from his defense to say, the caricature of what that meant. So you have a data center. The workload here is, solar there. That's the capacity of the data center. Cooling is in red, so this is a very efficient data center. Workload is in blue, and how can you run a data center off of something that looks like that? Well, the goal is to get it to look like this. And you have basically 2 tools. You have energy storage to try to shift demand to the right, where you can do it. So you save energy, and you have temporal flexibility in your workload to shift demand from overnight, the batch kind of archival tasks, to when you have energy available during the day. And so simple idea, highly controversial at the time. Industry did not believe that this was something that was possible or desirable or needed. And it was a lot of work by many of us in the community to try to get over that point and to realize visions of not just flexibility within the data center, but also flexibility across data centers, where you move workloads between data centers to balance carbon footprint, to balance electricity costs, to balance all those things. And so we started off at Caltech with Minghong, Lachlan, and Zhenhua, and Minghong's not here yet, right? I was hoping maybe he would get here just in time, but he'll be here tonight. And so Zhenhua's in the back, and this was their thesis when we started, and this was really something that I don't think I would have worked on if not for Stephen and the transition that happened at Caltech at that time to really focus not just on distributed systems and infrastructure, but to bring power and sustainability into the area, into our focus. And so, what's the algorithmic question that we focused on? In words, it's basically, servers use power even when they're idle, so you can't just move workload around and hope that power balances. And then turning them off fully is a big significant cost in terms of wear and tear. And so you need to, be able to do that in a smart way, but you don't know future workloads. Predicting wind and solar is challenging. Not all workloads can be deferred. Not all of them are homogeneous in terms of where they can be run. Moving costs and data costs and all of that matter. Lots and lots of complexities. And so, fundamentally, though, the core challenge is how do you know when to do something different with your system, adapt your system without knowing the future, given that there's a switching cost to adapting your system. And this led me to my love affair with SOCO, smooth online convex optimization. And again, I guess people are calling it the Stephen way. Right? My PhD was all in stochastics and detailed modeling of queues and schedules, and not the optimization perspective, the constraint perspective for dealing with these things. And I think hanging around at Caltech, I mean, we started that way. Minghong's first work on this was in that more discrete, stochastic world. But then, I think Stephen wore off on us, and we ended up with the online optimization viewpoint, which, turned out to be the right one for building practical systems. And so this was, the thing that I know, and many of you worked with me on in some form or another. You have a cost function that arrives online. You pay your cost for the action in any given round, but then you also pay a switching cost between them. We called it smoothed because we didn't know any better initially. And we later found out this was convex function chasing and related to convex body chasing, but when we started, we had no idea about any of that. And then as we moved on, we started connecting with a much deeper, older literature in online learning and online algorithms. And when we started, all we could do was scalar. So all we could do was one-dimensional actions. And the goal was to try to have a constant competitive ratio for one-dimensional actions. And this is still, sorry to everybody else in the room who's working with me, this is still, I think, the result that makes me happiest to think back at. And I still remember being on the whiteboard with Minghong and Lachlan, and when we first observed the property that led to this result, it was beautiful. And so this is the slides from that time, I think slightly adapted from Minghong's to change the font and everything. But we had this algorithm where you could basically compute online some upper and lower bounds for your action, and then you just were lazy between them. So you stayed at the same action unless one of the bounds forced you to move. So you went up, and now you could stay at the same action, but then you hit this, you can't stay at the same action, so you move the minimal possible to stay within the bounds. That was the algorithm. Clean, simple, you could compute the bounds very easily in an online way. Practical, you didn't need much history at all. And the beautiful thing was that this was easy to analyze because the optimal did exactly the same thing in reverse time. And so you had an algorithm that couldn't be optimal because you couldn't know when to fall off the bound going forward in time without knowing the future. But you had a provable connection to the structure of the optimal. And so there was this clean characterization of the optimal that led exactly to the algorithm design. And it was so beautiful, I think, that we got stuck on it, and it made it hard to go from one dimension to multiple dimensions, because you don't have this outside of multiple dimensions. So we kept trying to find some sort of lazy view like this in multi-dimensions, and it stopped us. But it was just beautiful. And so that was it. And then the question became, can you move beyond scalar? Can you do things with constraints? Can you do things with predictions? And that's where for a decade now, many people here in the room have made very nice contributions to generalizations and of this kind of work. And at this, I think it might enter into functions. I think Nico will talk a little bit about one of the generalizations that's still going on today. And so we'll hear a little bit about this, hopefully, this afternoon and tomorrow. But at this point, we can think about predictions, exact predictions, predictions with error, untrusted predictions. We can think about non-convex costs, delays. We can have multi-step switching costs. We can have a strong one-to-one mapping between this and control problems to understand competitive control. And it's amazing how rich this model turned out to be. And all of these algorithms then immediately apply to data center load management, microgrid management, all of those things in a very direct way. And so without that, even just with the first result, we were excited. And so that summer, Minghong and Zhenhua basically strategically placed themselves in companies to try to be the converters, to take the lens that you should care about power, you should care about energy to the industry directly, even though they were telling us they didn't. And so it was not an obvious choice, not an obvious win, but Minghong went to Facebook, Zhenhua went to HP. Facebook had done nothing at this point, so Minghong showed up and was like, you should care about power. And they're like, we have no idea how much power we even use. We're not monitoring, they're not measuring it. They had no data about anything internal around power at that point. So Minghong built their first power management system during his internship, but they were too far behind to then implement anything. They just got the data, and so then they spent time figuring out from the data at that point what to do. Zhenhua went to HP, they were a little ahead. So he was lucky enough that they already cared and had had data measurements at that company, and so he was able to actually get things deployed. And so that was a huge win. So he was able to get this style of algorithm deployed in what was the first net zero. It wasn't really net zero, but they claimed it was net zero data center. And so I dug up, have you seen this in a while? I dug up the dashboard from that first data center. This was what they had in terms of their internal visibility. And so they showed, like, let's see if it will run. It's not going to run. Drat. Too old. Copied it over. So it's not going to run. But, oh, it is running? Oh, good. Now it's running. Slowly? Started? Oh, just very slow. And so you can see it'll like show up. There's time of day up front. It'll show the sun. When it's sunny, more work will get done. And this was running on a real data center in Palo Alto, giving the dashboard for what was happening in that day with real production loads. And the big thing down here was the savings compared to running on grid was 78% for that day, which was a pretty typical savings. So. Zhenhua. It was an amazing accomplishment to get this to happen in a company at that point. And then we came back and we started working with Google, and this was then our dashboard for the next step, which was to go between data centers. And this was some Caltech undergrads put together the vision, and I hadn't seen this in a super long time. So let's see if it plays. Nope, it's not going to play. It was playing before. There we go. Oh, there we go. Okay. And so here, it's showing moving from the population centers, real workloads. The size of the line tells you how much load is going from there to which data center. The left side is the demand. The right side is how much renewable energy is available, and the red is the greed usage. And so if the right side is way bigger than the red side, you're curtailing renewables. If it looks like a nice circle, then you're doing a good job of adapting locally. And so this was with Google's sustainability infrastructure team at the time to sort of demonstrate the power of the algorithms to them there. Okay, and so we did some things, and then we turned, and this was Zhenhua in his thesis, we turned to demand response. And so this was part of the collaboration with Southern California Edison at the time, where we started to ask them, like, can you use data centers as a virtual storage facility in the grid? So can you actually get enough flexibility from data centers to make it worth your while in terms of replacing the need to install storage? And so we did some real case study with real workloads and everything, and we figured out that 20 megawatt data center, which is what a large one at the time, small compared to today, was kind of like about 700 kilowatt hours of storage, which saved 1 to 5 million at the time in terms of installing a storage. But this was a huge ask for a grid or utility at the time to think of actually deploying something like this. So this never got out of the case study phase in that world. The best we could do there was emergency demand response, which HP deployed in Fort Collins. But it was exciting, and despite the fact that things like demand response not happening at that time scale, this is an example of the big push in academia making a huge difference in industry. And so this was the extension of that plot that I showed you. So before it was cut off here, and everybody was talking about what it looked like for growth, you then had 7 years-ish of basically flat energy usage of data centers, not because demand shrunk. This line shows you what it would have looked like if there were not energy efficiency improvements in the data center. So basically all of this peak was carved off because of the academic research and partnerships with industry on data center improvements at that point. So I think it's a huge success story for research funding from NSF on a project that industry didn't care about stopping a huge, massive energy impact. So, but the true potential wasn't realized because while all those data centers and Metas and Googles and Microsofts made tons of sustainability pledges, and they're still making them today about how they're zero powered entirely by renewables. What that means most typically is that they pay power purchasing agreements. So they buy a bunch of offshore wind somewhere, and then they build a data center somewhere else, and they don't care whether that wind actually gets used. right? And so, there's a lot of studies as to why PPAs don't actually solve the problem, especially with data centers. But maybe the easiest way to see it is this is what CalISO shows in terms of curtailment of renewables. So, you're building more and more renewables, and you're curtailing more and more of them. So you're just wasting more and more of them. And this is not a solution. This is not making a data center more sustainable if you build a bunch of renewable energy that then gets curtailed. And so, yeah, especially that there's a huge opportunity, and the challenge and opportunity that comes with AI is that now we have a need. Go for it.
Do you know off the top of your head what the percentage of total energy produced is being curtailed?
Not off the top of my head. It's growing, not as steeply as this, but it's growing, and it's growing especially in your world, in the Northeast, actually. The wind is really leading to a lot of curtailment there. Okay, so then AI arrives, and this is now Andrew Chen's slide graph. I really like it because it shows how the projections have changed. So this is projection for electricity change in the sort of Northern Virginia area. So you see like the 2019 projection is flat, the this is 21 is flat, 22 goes up a little bit, 22 is there, and then you have this big jump in terms of the projections when you get to 2023. And so people have just been way off, and now there's massive growth coming. And this, because of data centers being as potentially integratable, the data center demand response work that Shenhua pioneered, now we have things, there's a need, right? So there's an opportunity and there's a need. And it's happening in industry in large scale. So Anna, who's been a collaborator of the group for a long time, since her PhD days, is now head of the sustainable research data center work at Google. And so she has deployed this for demand management. This is the Google blog animation, way nicer than we ever made in terms of doing the adaptation of the workload to when there's renewables. And grid integration isn't optional anymore. If you're going to build a data center in a congested utility, to be able to do it, you have to convince the utility you're going to be a partner in managing your demand. And so even big companies like Google, and this is again from Anna's team, are now doing demand response in their data centers that they're doing new construction. And so it tends to be peak shaving or ramp management. And so you take the evening load and you move it a couple hours later, and you help avoid that ramp problem, or you help avoid that peak problem right in the late afternoon. And so this is where my graduation, so my thesis defense. So this is, and we've also been starting to do this, and so we have a startup that's now out there, out of stealth mode, called Veris, that we're trying to really do this in a large scale way for hyperscale data centers as well. So we're going all the way from the theorems to the startup finally in this world. But there's still lots to do, and so actually yesterday our expedition grant was announced, and so Caltech is part of an expedition to work on exactly this problem, sustainable grid integrated data centers, and there's tons of work to be done there, but I won't go into that. I want to end with something sort of pure fun. I think this is an area where crazy ideas are probably the game changers that we need. And so if I used to have some really silly examples coming from back in the day. So this is a real patent around a floating data center. You just take barges, you put them out there, they get tidal energy from the waves, you just have them dragging on a line, which is your communication and back to the shore. This one never went anywhere, but the idea was to get old cruise ships and basically load them up with servers. This was my favorite one from one of Shenhua's mentors, and I helped to do the back of the envelope calculation with them, Chandrakant Patel. And so they tried to deploy this. So this is a manure-powered data center. You take the waste heat from the data center and you use it for the reaction of the manure to turn it into power, which then feeds back into the data center. It turns out all of that calculation works out just fine. The problem is that farms don't have high bandwidth. It's really expensive to get bandwidth to farmland, and so that was the killer challenge for this one actually. But you have a nice symbiotic reaction there that just churns out milk as its byproduct. So it's really cool. Underwater data centers, I also helped with the back of the envelope calculation for these. Microsoft deployed them for a few years. I don't know actually the status, but there's still some. I don't think they ever scaled up, but this was literally like stick them in submarines offshore a little bit. You don't have to cool them anymore. If something fails, oh well, you're gonna pull it back up in 2 years, and that's fine. So those were crazy ones. These days, crazy things are being suggested. OpenAI has talked about a nuclear powered campus. They recently bought a campus that is entirely powered by an old nuclear plant. And massive concentrated solar storage is really actually makes a lot of sense. So if you're going to have large scale energy storage on site, you heat up a bunch of salt, it generates, you save that heat, you have 4 to 6 hours of storage that is of a scale that can kind of be your backup for a data center. And so you can really integrate wild technologies into data center campuses and have it make financial sense when you're talking about gigawatt scale facilities. And then this one, I really like. This is a complete example of thinking outside of the box. This is a local Caltech, Ali Hajimeri, real patent filed, I think, 1.5 years or 2 years ago for a space-based data center. So the idea is you put it up on satellites, you do your compute up there. We have reasonable communication to get get it back at the end of the day. Heating, cooling isn't a problem. You just get it up there. It's a little one-time cost to get it up there, and then the management is free. And you might think this sounds really crazy, but he's already doing space-based power, where he's beaming power back from solar arrays in space. And so, it's not that outlandish, actually. So anyway, think out of the box, and I think this is a really fun area still, and fun again after 10 years of work in it. So thanks. Yeah, Harvey.
So, how much of this would happen if there were no GPUs and FPGAs?
Meaning, what would be the alternative?
Yeah, I mean, the point is that people like NVIDIA couldn't give a damn about the physics and the trade-off between societal impact and putting money not in making 1,000-watt GPUs, but investing more money in crossing the barrier where you have two-dimensional materials, you decrease the orders of magnitude of energy dissipation, and do that instead.
No, I think that's exactly right. You talk to people in Chen, right there, our neuroscience center, and they argue, this is much more power efficient than a GPU and does a lot of the same things. If we can learn from this and really improve the hardware, then that's a huge win here. I think that's right. I think there's huge wins from the hardware side, both in the compute, the storage, and the energy storage offsite and the memory on chip. Like getting memory close to makes a huge difference, because that's one of the biggest differences here. Memory is in situ with the computation.
I mean, the societal statement is, how much is this orientation towards dissipating more and more energy unacceptable?
That comes back to the what percentage of our society's energy should we put towards compute? Yeah.
Is there a parallel between what's happening in the crypto world with proof of work based mining, and I mean that also is a source of incredible energy demand, and how is that different from the consumption from data centers? And
I mean, actually, the crypto mining facilities are the biggest, in the last 5 years, were the biggest uptakes for demand response, because they're about making dollars from their compute, and if you pay them well enough to shut down, then it's just a trade-off between how much money they can make mining crypto versus how much money they can make from the utility adjusting their load. And so there are examples of crypto mining data centers really being very active participants in utility programs. That said, Europe is probably going to stop allowing crypto mining data centers to be built because of their assessment that it's not societally important enough to spend the energy on. And so there's going to be a sort of backlash along those fronts for it as well.
Last question, then we'll take a break.
So I'm curious, actually two parts. So the first one is, if you think about training large models, how much of an opportunity does that present? Because it is a fairly flexible load and can be interrupted safely. And then secondly, on your question of like, how is this aligned with societal benefit? Do you think there's opportunities for market mechanisms to like arrive at good solutions for that?
Yeah, I think one of the big changes is, when we started this, it was always a question, how much of Google's workload, say, is deferrable? And there was a big argument of, is it 10% or 50% or 30%? But now, when you're talking about OpenAI, how much is deferrable? All of it, right? You can really be smart in how you train, and building actually energy-aware mechanisms into the training, into the scheduler of the training is a very nice, active research area. There's also silly things like, typically, a training for an LM is, basically you think of it as a big burst while it's on, and then it's going to go off, and it's going to be on for weeks or months. And then from the utilities perspective, it has no idea of when this 1 gigawatt load is going to turn into 0, which is terrible. But it's even worse than that, because the way that neural nets are training and gathering and training and gathering mean that the energy alerts go like this during the whole period it's on, going from 100% to 20% over and over again, sometimes at a like second-level scale, and that is a disaster for a utility, right? And so they're really creating major challenges for utilities when they are nominally deferrable and easy, should be able to integrate into these programs. And market mechanisms, of course, really important. It's going to take different market mechanisms to align, AI training than it does to, consumer participating in the grid.
Thank Adam again. Thank you.